welcome Fereshte. Fereshte Shahbeigi already visited us 2 years ago. Now she's back in Krakow. Originally, she's from Iran. So now she's affiliated in Tehran, but originally she was from Mashhad, yes?
Yeah.
Largest city in the north east part of Iran.
Yes.
And she will tell us today about discrete and continuous Markovian evolution. So, Fereshte, please go ahead.
Thank you very much, and thanks all for being here. Yes, as it is kindly mentioned, I'm going to tell you what I did like 2 years ago and a bit about what I'm doing right now. And you can see here a list of my collaborators. Apart from those whom you know, there is also David, who is from Mexico, but now in University of Calgary. And he was a collaborator of us in our last project. And there is also Kurosh Sadri, my colleague at Sharif University of Technology. He's a bachelor student there, who is helping us with with our ongoing project now. Indeed, I can say I decided to provide you with a comprehensive introduction. So I kind of apologize to those who have seen these concepts thousands of times. But let me start with posing the problem. What is the problem we are going to talk about? So you can see this picture. This is an isolated system which undergoes a unitary evolution, and we can simply find the state at time t with Schrödinger equation probably, and through this simple function u rho u dagger. But an isolated system, a closed system, is an idealization which almost never occurs in reality. So basically, we are dealing with this situation in which the system of our interest is an open to an environment, and what we are looking for is to somehow describe type evolution of this system. Usually, we are not interested in the environment, or we do not have access to environment. We just want to know the evolution of the system. Of course, you know that the celebrated GKLS equation somehow provides us a way to describe such time evolution. But of course, it doesn't work like always, because the equation somehow is driven under very many indeed approximations and assumptions like weak couplings and everything. But if we put aside our dream of having an equation, a differential equation of motion, and just take the system and environment as a larger isolated system, and then find the state of this larger system at time t through, for example, Schrödinger equation, and then trace out the environment, we may come up with another approach, which is quantum channels. The only assumption here, as you can see, is that the state, the system and environment are initially in product state. So this is the only assumption, and it is completely different from the first one, in which we have many other assumptions as well. So despite this GKLS equation, specifically when terms in this equation, when terms in this equation are time independent, or this gamma is positive, despite this equation, such a picture provides us a broader description of the system evolution. So there is a natural question now. We are dealing with two different approaches here. And the question here is now when these two approaches are compatible with each other. Before I keep going, let me just provide you a short reminder of what is a quantum channel. Well, of course, you know it is a linear, trace preserving, and completely positive map. And it is very, very easy to indeed check if a map is quantum channels or if it is trace preserving and completely positive. And we can do it simply through this dynamical matrix or Choi matrix, which we can get by this equation in which psi plus is a maximally entangled state. And positivity of this matrix gives us the completely positivity of the map E. And if this function, this matrix also satisfied this partial trace condition, we can then be sure that the map is also trace preserving. So what I want you to remember here is that how easy it is to check if a map is a quantum channel. And also let me just, before I keep going with the rest, let me just fix the notation. In the whole presentation, I'm gonna use this correspondence in which we assign to a matrix, a rectangular matrix generally, but here we are mostly working with square matrices. Anyway, we can assign a vector to any such matrix through this correspondence. And so any rectangular matrix can be represented by a vector in extended Hilbert space, which also satisfies the Hilbert-Schmidt inner product. Applying such vectorization on both sides of Lindblad equations, we can Lindblad equations, which actually acts on a state of dimension n, then we can come up with a super operator for this Lindblad operation in the extended Hilbert space. So it is indeed a matrix of dimension n squared, which in terms of the parts participated in GKLS equation can be described through this simple equation here. If all terms here are time independent, then we can simply write a state at time t through these simple semigroup. We also want to apply this vectorization on quantum channels. So any quantum channel acting on n-dimensional systems then can be represented by a matrix of dimension n squared, which also has this simple relation based on the cross operators. And this bar here means complex conjugation. Checking if a matrix of dimension n squared is a quantum channel, then can be simply done by a special reordering of elements of phi, which is called reshuffling. So we can get that Choi matrix I showed you in the previous slide by reshuffling of the elements of the super operator corresponding to a quantum channel. This is the notation I'm going to use. So applying this notation, let me just restate the question we are going to discuss. So, yeah. Okay, the question is, we are given a quantum channel in the convex set of all quantum channels, and we want to know if we can find a trajectory started from identity and passes through this point, a given quantum channel at time t, and this trajectory is generated by a Lindblad generator. We want to know if such a trajectory for a given quantum channel exists. And if this trajectory exists, then we call this quantum channel a Markovian quantum channel. And specifically, this special question is called Markovianity. And these are some papers related to this problem. The first one introduced the problem of Markovianity, in which there also exists another nice theorem concerning this problem, which is actually an equivalent question, which we can work instead of Markovianity itself in the way I just mentioned. So the equivalent question now is, for a given quantum channel phi, if we can find the logarithm or the generator of phi such that this logarithm fulfills three conditions of hermiticity preserving, trace preserving, and conditionally completely positivity. So basically what we should do is to find just the logarithm of phi. And applying this theorem, we can also restate the problem of Markovianity in the following way. So we want to know for which quantum channel phi, the entire trajectory generated by logarithm of phi belongs to the set of quantum channel at each moment of time. And let me tell you, checking these three conditions is not difficult. I mean, once we have an n-squared matrix such L, we can simply check if these two conditions are satisfied. The third one might be a bit challenging, but please look at this operator in between. This is somehow analog to Choi matrix, but now related to a Lindblad generator and not to a quantum channel itself. So basically what we should do is to find L reshuffled and project this L reshuffled to n² minus 1 dimensional subspace and check if it is positive. So basically the difficulty of such condition is the same as difficulty of finding if a matrix is a quantum channel, which means it's not difficult at all. So we have a question, actually 3 different versions of the same question in this slide. And we have a way to answer this question. So everything's clear, apparently. But it turns out not only this problem is a very difficult problem to solve analytically, but also in this second paper, it has been shown that this problem from computational perspective is also an NP-hard problem. So the question is, what is so difficult here? Why it is an NP-hard problem? We are in the homeland of great mathematicians, so I can presume that everyone can identify where the problem is. But for the sake of completeness, let me just mention the origin of difficulty and complexity of this problem. The problem lies actually in the fact that in the logarithm. So let's assume a number, not a matrix. For a number z, logarithm can be written in this form. So we can see for different integers m, we can get different logarithm for the same number z, because for different integer m here, we get the same point in the complex plane, but for different integer m here, we do not get the same point in the complex plane. When it comes to a matrix, the problem becomes even more complicated. I'm going to provide you 2 simple examples here in the following, but let me just make it easier to just talk about this issue. We can say that X is a generator of A or is a logarithm of A if we can get A by exponential of X, as simple as it is. Now let's just consider this simple relation concerning Pauli matrices, which we are all familiar with. And let's take theta to be 2m pi. We can see then that identity can be given by this relation here, which not only for different numbers, integers m, which changes different numbers m, which change discretely, but also for different vectors n, which change continuously, we get different generator for identity. Also, there is always a very trivial generator for identity, which is 0. Exponential of 0 is always identity. And these are not all generators of identity. Let's just take have a look at another example here. And this is, again, identity at dimension 3. And we have this trivial solution for the generator, but also these 2 matrices here provide a generator for identity. And I specifically wanted to write this second example just to show you that there are also different real generators for a matrix. What is not very clear in my examples here is that because I worked with identity in both of them, generators commute with the original matrix, but it's not true always. In the general case, we can find generators for a matrix which are not commutative with the matrix itself. Also, we can find many generators for a matrix. We can find many real generators for a matrix. It depends on the spectrum of matrix. Indeed, the generator of a matrix can be considered to be unique if and only if the spectrum contains only positive non-degenerate eigenvalues. So the problem exactly is here.
Sorry, Fereshte. So
Yeah.
let's say X2, it is a real matrix. Of course, it's non-symmetric. So the eigenvalues can be complex, but we don't mind unless one eigenvalue is negative or one real eigenvalue.
No. The point is that if we want to find different generators for a matrix, the generator is unique when the matrix itself has positive non-degenerate eigenvalues. This is the generator which has complex eigenvalues.
Yes.
So the matrix itself has real eigenvalues, but it's not non-degenerated. This is the problem. Degeneracy cause problem here. Yeah?
Yes, thank you. Okay.
Yeah, sure. So, as I told, basically we can find many different generators for a matrix, many different real generators for a matrix, and these real generators are unique, and only real generators are unique if and only if the matrix itself has a real non-degenerated spectrum. And this is where the problem is actually. So because for a given quantum channel, we find a logarithm for a matrix, and we check if those three conditions that I showed you in the previous slide is satisfied. If they are satisfied, then yay, we find the answer. The quantum channel is Markovian. If they are not satisfied, then maybe another generator of the matrix can satisfy those three conditions. So we cannot say anything for sure. This is where the problem is. And before keep going with the rest, let me just mention there are different terminologies people use in the literature. Just let me summarize them in short. Though the problem of Markovianity, as I mentioned, was introduced in 2008, its classical counterpart is a very long-standing question, and still is a general open question for general dimension, which is called classical embeddability problem. This is the oldest paper I could find, but maybe the problem is even older than 1962. And it asks for a given biostochastic matrix, if we can find a Kolmogorov operator, which can be seen somehow as the classical counterpart of Lindblad generator. And then we can write this stochastic matrix as exponential of such Kolmogorov operator for some interaction time t. And there is also quantum embeddability problem, which introduced by Kamil in his recent published paper. I'm not sure if Kamil is here. I haven't seen, but he can correct me if I'm wrong if he's here.
Okay, we'll tell him that his paper was mentioned. I'm afraid he's not here now, but okay, we'll ask him.
So he cannot correct me if I'm wrong.
No, so it is correct. Everything is fine.
Yeah, okay.
And Matteo is his colleague who visited us just a month ago, also delivered a talk at this seminar.
Yes, I can remember that. Okay, quantum embeddability asks for a given stochastic matrix T, if we can find a quantum channel related to this stochastic matrix, in such a way that by super decoherence of this quantum channel, we can get this stochastic matrix. And if I have enough time, then I can tell you about this correspondence of super decoherence and stochastic matrices and quantum channels. But for now, just let's assume that these quantum channels are related to this stochastic matrix. And then these quantum channels are Markovian. And then they introduce a very, very nice application considering the advantage that we can get for these stochastic matrices if we simulate them in quantum regime and not in classical regime. The advantage concerns the memory, let's say space and time memory. There is also Markovianity problem, which we have been talking about up until now. And there is another version, which is very, very more simplified. In this last version, accessibility problem, we take a set of quantum channels and we assign to any member of this set a Lindblad generator in this way. Let me just mention that we can simply show that this map from quantum channels to Lindblad generators actually provide us a valid Lindblad generator. We can simply check that all those three conditions satisfy for these Lindblad generators, but not all Lindblad generators can be written as a quantum channel minus identity thing we have here. So we are given a set of quantum channels. We assign to any set of quantum channels to any member of this set a Lindblad generator, and then we ask which quantum channels lie on trajectory generated by arbitrary convex combination of these Lindblad generators. This, of course, is a very, very simplified version of the Markovianity problem, but I will show you why it is still worth working and asking this question. Okay, now let's back to our main problem of Markovian channel. In this talk, let me just mention that in this talk, we will be talking about these two versions more than these two, and maybe we can have a short discussion concerning the first one. Okay, about Markovianity problem, there are two mathematical nice theorems that can help us to provide a necessary but not necessary and sufficient condition. The first one states that if we have a hermiticity preserving operator, then this operator has a real representation in a Hermitian basis. The most familiar example for us is a quantum channel itself, because a quantum channel is hermiticity preserving, and we are all familiar with the Bloch representation of a quantum channel, which is actually the real representation in a Hermitian basis for a quantum channel. The second one, which is maybe even more important, states that if we are dealing with a non-singular matrix, actually a non-singular real matrix, then this real matrix has a real generator if and only if these two conditions are satisfied. So if there is a negative eigenvalue in the spectrum, then this negative eigenvalue should be evenfold degenerated. And if there are complex eigenvalues, these complex eigenvalues should appear in complex conjugation pair. We know that for a let's see how it relates to us. Look, when we are working with a quantum channel, we know that we have a real representation for a quantum channel. And since the Lindblad generators are also hermiticity preserving, as I mentioned some slides in some previous slides, Lindblad generators are also hermiticity preserving, so they also have a real representation. So if a quantum channel wants to have a real generator, it should fulfill these two conditions. The second one, we are sure that is satisfied for any quantum channel through the Perron-Frobenius theorem. But the first one provides us a necessary condition for a quantum channel to be Markovian. in such a way that if we have a quantum channel and its spectrum contains a negative, but not a negative even-fold degenerated matrix, I'm sorry, even-fold degenerate eigenvalue, then this quantum channel for sure is not Markovian. If the spectrum contains a negative eigenvalue and this negative eigenvalue is even-fold degenerated, then we cannot say anything. So this is only a necessary condition and not necessary and sufficient. Okay, let's check the simplest example we always want to deal with. And this is, of course, Pauli channels, which are given in this with this relation. We can find the superoperator of these Pauli maps through this relation, which gives us this matrix. This is, as you can see, is a Hermitian matrix. So we can simplify the eigenvalues, eigenvectors, and everything. And actually, eigenvalues are given through these relations here. Eigenvalues are real because we are dealing with a Hermitian matrix. There is always an eigenvalue equal to 1, a leading eigenvalue, because the map is trace preserving, but there are also 3 other eigenvalues which can be negative and positive, but they are embedded inside a tetrahedron like this. And if we want to take into account what we have already seen, we may notice that the center of cube and the center of tetrahedron are the same. So basically, we have valid Pauli channels in all the octants of the space, which means there are Pauli channels which have all eigenvalues, all positive eigenvalues, these 2 positive eigenvalues. There are also Pauli maps for which there is 1 negative eigenvalue and 2 positive ones. There are maps with 3 negative eigenvalues, and there are maps with 2 negative eigenvalues and 1 positive eigenvalue. Which we, if we actually applied that necessary condition that we saw in the previous slide, then we can say actually for sure that if there are Markovian channels, they should be in the octant of a space, in the positive octant of a space, or in the negative ones in which there are 2 negative eigenvalues. And if there are Markovian channels, Pauli channels in these octants of the space, then they should actually lie on the bisectors plane of those octants, because they should be even-fold degenerated. Indeed, these are the set of Markovian channels in the tetrahedron of Pauli channels. And this is the figure I got from this paper here. And what they did is to actually discuss all different logarithms for Pauli channels in the tetrahedron here. And this fairly simple related to other examples we can work with, because as you saw, the matrix is Hermitian, and since like they always are 2 eigenvalue equal to 1 in the spectrum, then we can simply discuss all different generators for the maps. The necessary and sufficient conditions they found through all that indeed the investigations with all those generators of Pauli channels is this 3 conditions for a quantum channel with positive eigenvalues, and this indeed this single condition for channels in which there are 2 negative degenerated eigenvalues lambda, and of course 1 positive one. If we apply these conditions, then we can simply get this shape here, in which you can see 2-dimensional planes corresponding those bisectors we will just discussed of quantum channels with negative degenerated eigenvalues. And this body here, and it has a volume indeed. This is the subset of Markovian Pauli maps with all 3 eigenvalues, all 3 non-trivial eigenvalues, which are positive.
Sorry, first, maybe it's
Yes.
good to label one corner which is distinguished because it corresponds to identity, because otherwise it's not so clear. So this is identity, and other Pauli matrices are,
Yes.
yes,
This is X. This is not plus.
yes, X,
Yeah.
Y, Z. And
Yeah.
now, so maybe you could try to explain those green hairs, or not hairs, but wings, or how is it?
Uh-huh. Um,
Because it's not
okay.
so easy to see, but the first part on the upper right part is three-dimensional.
Yes.
Uh, yes,
Okay.
this light green.
Yes. Yes. The light green is the three-dimensional.
Has some volume.
Yeah, it has some
Yes.
volume. I will mention that. And these three two-dimensional planes are corresponding to those channels with negative eigenvalues, but negative degenerated, and that's why they are two-dimensional.
Mhm. And they join this set with three corners, which correspond to Pauli matrices or Pauli
Themselves.
generators, sigma X, Y,
Yeah.
and Z. Yes.
Yes, yes, yes. And they
Yes.
also,
Yes.
this is the exactly the center of tetrahedron corresponding to maximally depolarizing channel.
Yes.
Okay, now let's see what are the properties of these Markovian Pauli channels in this tetrahedron. So, and these properties I'm telling you from this paper, not from that paper that I took the figure from. Okay, first of all, I'm going to show the set of Markovian channels, or maybe now later I will tell you this is the set of accessible maps, but here we can also take that to be the set of Markovian channels with this notation here, AQ2 of, okay, this subset is non-convex, of course. This is a very well-known fact that the set of Markovian channels is non-convex, but it is star-shaped with respect to the line connecting identity to the center of tetrahedron. What is a star-shape means? So we are given a quantum, we are given a set which is not convex as here, because of course it's not convex, we can see, but we can find some points in this figure, for example, these points. For these points, we can see that the convex combination of any points of this set with a point on this line lies in the set. So this set is called to be like a star shape with respect to this line here. And the set of Markovian channels is star shaped with respect to the line connecting identity to the center of tetrahedron. And of course, there is no channel on the surface of tetrahedron. So all Markovian quantum channels are even on the edges, on the vertices, or inside the tetrahedrons. The set of Markovian channels here are uniostochastic, which means that they fulfill this relation in which we can get the environment to be like maximally mixed state. Not all quantum channels are uniostochastic, but if we can get the environment to be maximally mixed, then we can get the subset of uniostochastic channels, which are introduced in this paper. And these two conditions provide the necessary and sufficient condition for Pauli channels to be uniostochastic. You can see that these two conditions are exactly the same as the one I show you in these necessary and sufficient conditions of for being Markovian. But here we don't ask them to be positive always. So here we can also have negative eigenvalues. And exactly this set here with all those dark and light colors, this set shows the set of uniostochastic Pauli channels. And this dark part here is the subset of Markovian channels actually the three-dimensional subset of Markovian channels, because there are also some two-dimensionals which are now inside these three parts. And this is actually what we could see before. I think we all saw it sometime in Carol's office.
Yes, so a short comment. So this was a 3D outprint done by colleagues of Zbyszek, I presume, in Gliwice. So I'm very, very pleased that they did it. But now I have a simple request for help, because this nice device or somehow
Yes.
disappeared. If
Yeah.
somebody of you ever took it, please, or has it, please give it back or tell me where it is, because we lost the control over this fancy exponent. Yes.
Yes. Yes. Yes. Thank you. And if we take, actually, if we want to know what is the volume of Markovian channels, and please notice that I'm talking about Markovian channels. The volume of Markovian channels in this set of whole Pauli channels is just 3/32. The exact number, so like 9%, approximately. Okay. But actually, I should mention again that the whole volume of the set of Markovian channels are given by this three-dimensional subspace here, because these two-dimensional planes have no volume.
No three-dimensional volume.
No three-dimensional volume, yeah.
Yes.
So let's just concentrate on this main Markovian channels, which provide us the volume. Okay, this is again the Lindblad generator. And let's assume that we take Hamiltonian to be identity or zero, and we take gamma j to be like a delta function, and these jump operators to be one of the Pauli maps. So we get like three different Lindblad generators, Lx, Ly, and Lz, and corresponding to each of which we can get a dynamical semigroup. The point is that any point on the boundaries of these Markovian channels, actually any points on the boundaries of these three-dimensional subspace of Markovian channels, can be gained by choosing like two out of these three dynamical semigroups. So we can just take like T1 or T2 to be non-zero, then we get a point on this surface. If we get like T1 and T3 to be non-zero, then we get a point on the surface of Markovian channels. And of course, if we get Ty and Tz to be non-zero, then we get T2 and T3 to be non-zero, then we get a point on the surface that we cannot see. And if we want to get a point in the interior of this two-dimensional object, then we can have all those three interaction times to be non-zero, and corresponding to each point in this set, we can find a very, very unique actually combination of T1, T2, and T3, which are given by the eigenvalues with this relation. And the necessary and sufficient condition for a quantum channel to be located in this three-dimensional object here is that this part to be positive. And as you can see, this is exactly what I just told you about accessibility problem. So we have a set of quantum channels, we assign to this set a Lindblad generators, and then we have this complete set of quantum channels which can be gained by let's say exponential of those Lindblad generators. So this set is actually can be gained with accessibility of just a very, very limited set of quantum channels here, which makes the problem very, very easier. So motivated by this and the fact that now I can call this set, this subset of Markovian channels, which has the whole volume, subset of accessible maps, and this is why we showed that by A. Okay, now motivated by this, we can generalize these results to quantum wave channels, and quantum wave channels are actually unitary generalization of Pauli channels. So we have a unitary operator UKL, which are defined by x to power k, z to power l for different k and l from 0 to n minus 1, in which x is just the shift operator, changing I to I plus 1. In this, O plus means addition modulo n. And z is correspond actually counterpart of sigma z in 2 dimension, and just is a phase by combination of which we can get n squared unitary operators, which actually form a basis for the Hilbert-Schmidt space. And now we can just define the generalization of Pauli maps with convex combination of these unitary operators in this way. And again, we can see, well, these maps here are not anymore for higher dimensions. For if we put n equal to 2, then we get Pauli, the set of Pauli channels. But if we get n to be anything but 2, then we get larger sets. This larger set is not like Hermitian always, but we can see that they form a set of normal matrices. They are diagonalizable by unitary evolutions, and we can simplify the diagonal form of phi. There is actually a complex Hadamard matrix H, which we can apply by H on this probability vector here, and then we get eigenvalues. And if we apply H to these eigenvalues, then we can get probability vectors, because H here is self-inverse. So we can simplify also the diagonal form of Weyl channels. Now, actually, just like in Pauli channels, we restrict ourselves to very, very special Lindblad generators corresponding to each of these unitary Weyl operators, and then we define the set of all dynamical semigroups generated by a an arbitrary convex combination of these Lindblad generators, and then we ask which quantum channel lies on trajectories generated by these Lindblad generators. And if you consider here more precisely, you see that I am talking about phi of p, which actually are Weyl channels, and I haven't proved that if we take the set of Lindblad generators in this form, then we can only produce only Weyl channels. So the trajectory lies in the set of Weyl channels, but they do. So indeed, we can ask which quantum Weyl channels lie on the trajectories generated by these Lindblad generators. And well, I don't want to mention many technicalities here, many mathematical relations. There is indeed a very simple recipe that we can check if a Weyl quantum channel lies on such trajectory. So what we can do is that we are given a Weyl channel, so we basically know the probability vector. Then we can apply on this probability vector by the Hadamard matrix I showed you, and we get the eigenvalues, and we check if eigenvalues satisfy this relation. And if you have a look at this interaction time here, this is exactly this T mu appears in the dynamical semigroups. So if we can make sure that this relation is positive for any mu between 1 and n squared minus 1, then not only we can find if we can find that this specific quantum channel is accessible or not, but also we can say how we can reach or have access to this quantum channel through this Lindblad dynamics, because this is exactly the interaction time. And if we want to just check again the properties of the set of accessible, actually veil accessible maps, we can see like Pauli channels are again dealing with a non-convex but a star shape, well, with respect to the maximally depolarizing channel. Again, the set of accessible veil channels is log convex, and the log convexity lies in the fact that like Pauli channels, also all veil channels, we can show with this matrix here, all veil channels are commutative, exactly like all Pauli channels. So all Lindblad generators are commutative. So this fact actually results in the nice property that the set of accessible veil channels is log convex, which means they have a logarithm which is convex. And again, we can find the boundaries of the set by taking like at least one of those interaction time to be 0. Then we get like n squared minus 2-dimensional boundaries. If we take 2 of those interaction times to be 0, then we get n squared minus 3-dimensional boundaries, and so on. And if we want to get in the interior of the set, then we should have the whole interaction times to be non-zero. And against, actually, despite the Pauli channels, we could show not all members of the set of accessible maps are unistochastic in higher dimension. It is just the property we could see for Pauli channels. But again, we see that like Pauli channels, actually not all quantum channels with any rank can be accessible. I just may remind you that Markovian Pauli channels could be of rank 1, 2, or 4, not 3. And here we can also see this property holds. Not all ranks can be accessible. Well, if we take n to be equal to 2, then we are dealing with 3-dimensional object, those tetrahedron of Pauli maps. If we go to n equal 3, then we are dealing with n squared minus 1, so 8-dimensional object. We cannot show how it looks like, but we can have a cross section. So here we are dealing with Q-treat channels, Q-treat veil channels. This is the cross section formed by identity, one of the veil maps, and its dagger. So phi mu and phi mu bar actually shows that if it's phi, then it is phi dagger. This cross section, in this cross section, we have accessible maps, which shows, for example, veil channels can be of rank 1 and rank 3. At least we can get it from this figure, but there is no rank 2, because for any phi there is phi dagger, but we can conclude from this figure. Okay, of course, we can simply also show that accessible maps can be only of rank 1, 3, and 9, and there is no rank 2, 4, 5, 6, 7, 8. Also, another nice property for the veil channels of rank 3 is that if we take into account just the spectra of the veil channels, of the whole veil channels, and not those channels which are in this, let's say, cross section, then the spectra of the veil channels, of Q-treat veil channels, lie in the triangle specified by 1 unity omega and omega squared. And if we want just to take into account the whole set of accessible veil channels of dimension 3, then the spectrum of them, the spectrum spectra of the accessible Weyl channels embedded inside exactly the same shape with the same boundaries with the same relative volume, but in the complex plane. This is a cross section in the set of quantum channels, but this is only the complex plane, and we have the same shape for a spectra of accessible maps and for the accessible maps in a cross section formed by identity phi and phi dagger. Okay, the relative volume in this cross section is about 22%. We actually have the exact number, but well, let's say just 22%. And in the whole set of Weyl channels of dimension 3, Q-treat Weyl channels, the relative volume of accessible maps is only 0.09%. I may recall you that for Pauli channels, it was 9%, and now we have 0.09%. So it's reduced. Okay, may I know how much time I have?
You have like, 10 minutes. Or
10
even,
minutes.
yes, about.
Okay, yeah, I hope. Okay, let's now talk about super decoherence. Okay, we know that in the head of any quantum states, there is a classical state lies on the diagonal elements of any density operator. We can find a probability vector, which we can have access to by simply decohering the quantum state. Now we can have an analogous process on a quantum channel, and then extract a classical stochastic matrix from each quantum channel. So what we should do is to form the, let's say, Choi matrix related to any quantum channel, then decohere this Choi matrix, and just through this simple correspondence here with diagonal elements of a stochastic matrix, of a Choi matrix, we can find a stochastic matrix. So basically, we just show that with hyper decoherence of a quantum channel, we can get a classical map, a stochastic matrix. If we are giving the set of cross operators, then through this simple relation, we can get the stochastic matrix, which lives in the head of any quantum channel. Now we want to apply this super decoherence on Weyl channels. What we get is very, very, very amusing, actually, because we can see that this UKL was x to power k, z to power l, but we can see that z cannot play a role in the set of stochastic matrices obtained by hyperdecoherence of quantum channels. Indeed, this x to, I may remind you that these x and with different powers were only the cyclic permutation. So basically what we have here is the convex combination of cyclic permutation. These specific stochastic matrices, which are also biostochastics, are called circulant biostochastic matrices. And if you have a look at this simple example, if we have the first column or the first row of this matrix, then we can get all other columns or all other rows by simply just cyclically by cyclic permutation of the first column, and then the third one is gained by the cyclic permutation of the second one, and so on. This actually, the set of circulant biostochastic matrices is a subset of dimension n-1 in the Birkhoff polytope of dimension n-1 squared. And just like quantum channels, Weyl quantum channels, which we could find a Hadamard matrices, a Hadamard matrix. Here we can find a Fourier transformation, which by applying which on the probability vector here, we can get the eigenvalues of the stochastic matrix says here, and if we apply F dagger on this eigenvalues, then we can get probability vector again. Indeed, we can find the set of circulant biostochastic matrices simply in the set of in the matrix representation of Weil channels themselves. Look, this is the simplest case of Pauli channels. Weil channels contains of all Weil channels in any dimension are black diagonal. Each block is circulant, but not necessarily biostochastic circulant. But we can always find a biostochastic circulant matrix in one of these blocks. Here you can see in the outer blocks, there is a circulant biostochastic matrix. And this is actually the circulant biostochastic matrix, which we can get by hyperdecoherence of Weil channels themselves. So it is not very unusual or very strange that we can see this similarity between these circulant biostochastic matrices and Weil channels themselves. And now, like the Markovianity problem, which we restricted our, like accessibility problem, which in which we restricted ourselves to some specific Lindblad generators, we now define this set of specific Kolmogorov operators, and then we form all trajectories we can get by convex combination of those Kolmogorov operators, and then we ask which stochastic matrices lie on the trajectory generated by these dynamical semigroups. And again, like quantum Weil channels, there is a very, very simple recipe. Again, when we are given a circulant biostochastic matrix, which means we know the probability vector, we can get eigenvalues by applying Fourier transformation on probability vector, and then we can check if this relation holds for different eigenvalues. And again, we can see that if it holds, we can not only make sure that we are dealing with an accessible stochastic matrix, but also we can simply find the interaction time by which we can have access to this specific stochastic matrix.
I'm sorry, Fereshte?
Yes.
So there will be like less than 5 minutes, but here you have sum over nu, and it should be mu nu or mu n. There's something.
N, sum over n. I'm sorry.
Okay,
It's
yeah. So we
n.
sum over nu. Okay, good.
Okay, and it's well, again, it's not very, very amusing that the properties of the set of accessible stochastic matrices be like their quantum counterparts. So again, the set is non-convex, star shape with respect to the center, to T star, which sends all probability vectors into the maximally uniform probability vector. The set again is log convex. This is because all those generators we are working with are commutative. Again, we can get the boundaries of the set by fixing at least one of those interaction times to be 0, and we can get more boundaries with different dimensions if we just put different interaction times to be 0. And again, not all accessible maps with any rank can be accessible. And the most important point here is that we defined two different questions and we solve them independently in the set of quantum channels and in the set of biostochastic matrices. But then we can see that as quantum channels and circulant biostochastic matrices that can be related to each other through hyperdecoherence, these two sets of accessible circulant biostochastic matrices and quantum Weil channels accessible can also be related to each other with hyperdecoherence. So basically, if we wanted to get the set of accessible circulant biostochastic matrices, it was enough for us to just dephase or put those accessible Weil channels in the hyperdecoherence process. Oh, okay. Now for the set of accessible maps, since the space is n-1 dimensional, I can show you exactly the set and not the cross section. But as we can guess, again the shape of circulant biostochastic matrices in this plane, in this triangle, is exactly the same as the shape of the quantum Weil channels in the cross section of identity phi and phi dagger. And again, the spectra of these quantum channels, I'm sorry, the spectra of the whole set of circulant biostochastic matrices embedded inside a tetrahedron, but the spectra of accessible circulant biostochastic matrices embedded inside this heart shape again with the same boundaries and the same relative volume. But since we are dealing with n-1 dimensional subspace, I can also show you a actually the case for n equal to 4. I may remind you that the analogous quantum case would be of dimension n squared minus 1, so 15-dimensional subspace, but for classical maps, it is n-1 dimension, so we are dealing the set of accessible maps, which has a very, very strange shape. And this is actually, we can see again that this set is a star shape with respect to this point and all those properties I told you. But what is very strange here is the asymmetric shape of this. I actually presented this work at Shaykh University, and my supervisor Wahid there asked me to about these shapes, and then I plotted them and I found these pictures. This is an answer to Wahid, but this is actually a starting point for our ongoing project. We see this, let's say, asymmetry in this figure, and we may just consider why it is asymmetric. Why is so special about this edge, but not about these two edges? So we know why it is very, very special. What is so special about this vertex, but not these three vertices? Because identity is distinguished, because every trajectory started from identity. But what is so special about this edge? So if we just have some time with this problem, we can easily find that identity x squared and x to power 3 forms a group. And identity n x squared is just a subgroup of this group, but identity n x to power 3 is not a subgroup, and identity n x is not a subgroup. So we have, so the group only has one subgroup of dimension 2, and we can see there are accessible maps of the same rank on just one of the edges. And the group has one trivial subgroup of dimension 1, which we can see there is only one distinguished quantum accessible channel. I'm sorry, not quantum, but accessible stochastic matrix of or of rank 1. And then the group has a subgroup of the trivial subgroup, which is itself, so a group of a subgroup of cardinality 4. And then we can see that there are accessible maps of dimension of rank 4. So basically now we can somehow find an answer to the question of which maps by which rank can be accessible. So we can see that if the set which we are working for and by which we define the set of Lindblad generators form a group, then the rank of accessible maps are exactly the same of their cardinality of different subgroups we can write for this set. And there are also some other figures for different groups we can find in the set of quantum channels. So we may work with a group of order 2. It is only a cyclic group, and then we can see accessible maps lies on this segment of the line. If we work with a cyclic group of dimension 3, then we are working in this triangle. And if you just remember, I told you in the set of quantum channels, the cross section was corresponding to identity phi and phi dagger. And identity phi and phi dagger is actually when phi is a Weil channel, is actually a group of dimension 3. So it was not very strange to get that specific subset for accessible maps. And again, this is the spectra of this set. And if we work with a cyclic group of order 4, we get in which all elements are linearly dependent. We get a square. If we are working with a cyclic group of order 4, we get a pentagon, and so on. And always we can see that though these pictures, these photos are providing us a cross section in the set of quantum channels, the spectra in the complex plane are also completely comparable with these sets, but in the complex plane. And if we work, and these two figures actually shows us two different groups of dimension 4, a cyclic group, which we have here, and a non-cyclic group, which we have here. So here, when we work with a cyclic group, we only have a subgroup of dimension 2. But if we work with a non-cyclic group of dimension 4 of cardinality 4, then we have 3 subgroups of dimension 4. So we have accessible maps of all those edges. And also we have accessible maps with full rank, which is corresponding to the group itself, and this very specific accessible map of rank 1, which is corresponding to identity, the trivial subgroup of dimension of cardinality 1.
Yes,
Yes, this is the conclusion.
Yes.
Yeah, yes. I'm sorry that it takes so long. Anyway, what we had is we worked with the set of quantum channels, and we know that by hyperdecoherence of quantum channels, we can get the set of stochastic matrices, but we also have the set of unital quantum channels, which sends identity to itself. They are only a subgroup of the set of quantum channels. And by hyperdecoherence of unital quantum channels, we can recover the set of bistochastic quantum channels. We worked with the set of Weyl channels, and by hyperdecoherence of which we get the set of circulant bistochastic matrices, and we define for this specific set we actually solve for this specific set of Weyl channels the accessibility problems, by hyperdecoherence of which we can exactly get the set of accessible circulant bistochastic matrices. And thank you very much. Now that it is very difficult time to travel, I should thank you with a virtual visit of Iran. And yes, thank you.
Yes, thank you very much. Thanks, Fereshte, for telling about previous project and new one, and showing such nice pictures also with Iranian mountains. So let us start the discussion. Who would like to start?
I have a very trivial question.
Yes,
perhaps, concerning this, generator of a matrix. At the very beginning, really, is this ambiguity with the logarithm the only one? I mean, that you can add to pi to the eigenvalues or something. Is it the only possible ambiguity in this problem, or
here there... you mean?
Yes, exactly.
Or okay, which one?
No, really. I mean, just the most general
problem. No. There are much more.
Okay.
No, yeah.
So there's infinitely more, yes.
Yeah. Sometimes we can sometimes we can find real generators which are continuous.
Okay, I see. Perhaps when they are the generator or something.
Yeah.
I have a question.
Yes, please.
So this seemed like very nice work. It's really cool. I wonder, like what's next? Where does this lead to? Are there some interesting open questions you have remaining, or yeah?
Actually, what we are working now is on this group structure. We have many open questions now to work on. For example, what is very maybe what is not emphasized very much is that I showed you why we are working with the set of accessible maps and not Markovian channels. Yes.
Okay.
because Markovianity is a very difficult problem. On the other hand, accessibility seems to be very easy. They could recover the whole volume of Markovian channels, but only for Pauli channels. An open question for us now that is somehow stuck in my mind is to show that for other examples also accessibility can be a good approximation of Markovianity, because otherwise it doesn't seem to be very very productive. You know what I mean?
Okay.
Yeah,
so
this is
one
just
more remark. So Fereshte, we could claim it is an approximation of this set of Markovian channels from inside. And in the case of 1 qubit channels, we get the full measure, not entire set, but we describe in this way full volume of the set, yes? Up to some singularities.
Yes.
And now for other cases, we wish to somehow describe what we can, yes?
Yes. But it would be very nice if we can show that they exist, they still recover the whole volume, or at least a number very, very close to the whole volume. And maybe for the last remark, I should say that the volume of Markovian maps is not so large in the set of quantum channels. For example, if we take into account like all qubit channels and not only Pauli ones, then this volume of the Markovian maps is only 2%. And I'm talking about Markovian maps, not accessible maps. But still, it's nice to get a good results concerning the volume.
Remark, perhaps the last remark. So Kamil is not here somehow, but he also worked on the case for stochastic matrices, not bistochastic. So what happens if we now release the assumption that the channels or matrices are unital and go away from bistochastic to stochastic, quantum and classical?
I discussed the problem with Kamil. I think the problem Kamil is working on has two complexity origins, not one. Because I told you why the Markovianity is a difficult problem, because of the non-uniqueness of logarithms. But the problem, let me just show you again this slide. Not here. The problem that Kamil is working on, I think, is this one. And we have a non-uniqueness for logarithm here in this equation. But the problem Kamil is working has also a non-uniqueness here. So we can find different quantum channels for any stochastic matrices. And then we should just check the Markovianity problem for each of which. I think this is the main problem, maybe the main difficulty they should overcome. The fact that they are not bistochastic is not so relevant.
Okay, thank you, Fereshte.